is an important process for these massive galaxies. So then let's come to predictions of the mass function. So again, Paul showed us some work. I'm going to repeat a slide from his in just a second. But first, here is a mass function from a semi-analytic model applied to the Millennium simulation. And you can see at late times, especially at the high mass end, this significant growth in the mass function. So that is, again, what you would expect from hierarchical assembly. Here's the set of mass functions that Paul just showed us. So from a hydrosim, you see something that's very similar. So I'm interested in this growth here, especially at highest masses. Do we actually observe it? The answer is not yet. So here are observed mass functions now from the Primus survey. So this is from John Moustakis' work a few years ago. And you're looking at different panels or different redshift bins. So low redshift, this is Sloan, going all the way out to redshift 1. And the fit to the Sloan data is the solid line. And that's repeated in all the panels. So if you want to look for evolution, you want to compare the solid points to that line. And you can see there's really no evidence over this redshift range for an evolution in the mass function. But we've got some problems. At the high mass end especially, we're really limited in the statistical power of these kinds of data sets. So at low redshifts, we just don't have massive galaxies in the sample. The volumes are too small. And where they do appear, you can see that the error bars are very significant. That's both Poisson, but also sample variance issues coming in. So you actually wouldn't expect to be able to detect the predicted signal with the current data. And in fact, you can estimate that we really need something like 100 or even hundreds of square degrees before we could try to approach this problem. The good news is the data sets that are going to enable this are on their way. So we're really entering this era of wide field surveys, which I think would be very exciting. So let me just schematically illustrate my view on where surveys stand. So this is from a few years ago, let's say. We've got the Sloan Digital Sky Survey, very wide area, incredible volume, but not very far in distance, right? Not very high redshift. And then you have a series of pencil beam surveys. These are just a few square degrees, and these are the surveys that you know and love: Primus, D2, Cosmos, Candles, etc. This is what you need to do if you want to reach redshift 1 or even beyond. But you can see the volume in here is really tiny, and this has been the problem. So in recent years, BOSS, I think, has changed the situation. So now with BOSS, we can reach to redshifts of 0.6 or 0.7, at least for the most massive galaxies, and I'm going to come back to using the BOSS data in a little bit. But what's truly exciting is to consider these deep, wide field imaging surveys that are now online. Hypersync PrimeCam, I'll talk about a little bit later. HSC, DES is also observing. So these are going to cover thousands of square degrees, but with depths that allow you to track galaxy populations at least out to redshift 1 in a statistically complete way. So that's really going to address some of these questions. So I've been trying to make some inroads on this topic. And so this is really kind of early days, first steps in trying to utilize these wide field surveys. And so what I've done is create what I call the BOSS Stripe 82 Massive Galaxy Catalog. So I'm focusing on this famous Stripe 82 region. It's about 170 square degrees. This is covered by BOSS. It was also imaged multiple times by Sloan. And so as a result of that, the depth of this data is about 2 magnitudes deeper than the Sloan single epoch data. And there's lots of other data sets that fall in Stripe 82 as well. So for what I'm interested in terms of estimating stellar masses, the near-infrared coverage from UKIDS is especially important. And so I've developed a technique to try to match photometry in different data sets. This is important because when you get to hundreds of square degrees, the traditional methods for matching photometry across different bands and different telescopes become very tedious. So it's important to have ways that you can do this faster and robustly. So applying this so-called synthetic aperture magnitudes, I'm able to get 9-band SEDs. I can fit these and derive stellar mass estimates. And I've been trying to explore the systematics as well in those estimates. So in the interest of time, let me just show you the result that we have from this data set. So we're really zooming in with a very high mass center mass function. And I'm skipping a whole lot of challenges and details here, but let me show you the result. So these are mass functions from the Stripe 82 data set. There are 4 redshift intervals that are overplotted, and they run from a redshift of 0.63 to 0.35. So this is not a very large redshift range, but you can see the errors here are tiny. And so even over this relatively narrow range, you would expect to be able to detect evolution. And we don't see any signs of evolution so far. Just to emphasize that with this data set, out of these redshifts, this is nearly the Sloan 1 volume. So we're finally getting to the volumes that we need, but we don't see evolution. Okay, so what is going on? Right? We have clear predictions of growth in the mass functions. We have these observations that suggest growth in size. That seems to be consistent. But when we go out and look for growth in mass, we're not finding any evolution. So what could we be missing? So I think one answer to this is that we're just beginning to appreciate that these massive galaxies are really best described as multi-component systems. And they have likely outer envelopes and wings that have not been properly taken into account. There's a lot of people working on this subject. I just wanted to highlight some results from a paper that Benedetta Volcani and I worked on a few years ago. And what we did is study massive central galaxies in groups at moderate redshift, and we tried to look at slices of their fundamental plane. What we discovered is that by fitting the HST imaging data we had with multi-component fits, we could get size-mass relations where a fraction of our sample really appeared distinct from a control sample. But when we looked at other slices of other scaling relations that were more sensitive to the core components of these galaxies, we found very little difference. We couldn't tell them apart from the control sample. So when we looked at these data and compared them to cluster data at lower redshift, our interpretation was that this was evidence for the growing of outskirts, faint low surface brightness, wings in these galaxies is really driving the inferred size evolution. And I think there's, again, a lot of different works pursuing a similar story from a variety of angles. So this is important because it offers a potential solution to the problem. I think the hypothesis here is that the imaging data that we have used to measure mass and luminosity functions just hasn't been deep enough to accurately detect and characterize these low surface brightness outskirts. And in addition, we're using kind of crude tools to estimate light profiles, which are probably not sensitive to these outer components, which may be exactly where a lot of that mass assembly is taking place. So the good news is that I think these big surveys that are coming are going to really address this. So let me just say a few words about Hypersynchronocam survey. This is a 1.5 degree imaging camera on the Subaru 8-meter telescope. And the survey began a couple of years ago. The wide component of the survey is 5 bands to depths equivalent to the cosmos field, which was only 1 square degree, but now over 1,400 square degrees. I think it's really going to be transformative. And already, we're quite excited about the early data. So here are some massive central galaxies in the HSC data on top compared to the Sloan data on the bottom. And probably if you're close enough to the screen, you can start to see these low surface brightness regions around these massive galaxies. This is some preliminary work from Song Huang, where he's showing a radial profile for individual galaxies. These galaxies have not been stacked, but we are detecting light all the way out to 150 kiloparsecs in many cases for these systems, which I think is really impressive. So in addition to using imaging, I think there's a big role for IFS surveys. So you can see I'm bringing things back to manga. So of course what you would like to do locally is be able to confirm that these outer components have actually been assembled at different times, and that the stars in those components have a different assembly history than the cores of these massive galaxies. So I'm showing some plots here from Jenny Green that you're probably familiar with, gradients in age, metallicity, and abundance ratio for a sample of about 100 galaxies from the massive survey. And I think she's already starting to find some evidence in support of this picture, but just looking at the data, you would really like to have better statistics. So Manga, Sammy, and other surveys, I think, are already going to start having a big impact here. In the Manga data currently, we can redo this analysis with about double the sample. So I think this is right for the taking. Let me just wrap up with a little update on Manga. So as you heard from Rinbin and from others throughout this week, things are going well for our survey. We're on track to reach our goal of 10,000 galaxies by the end of 2020. These are some basic information about the data. Their spatial resolution yields something like 1 to 2 kiloparsec resolution for the galaxies in our sample. The spectral resolution is about 60 kilometers a second. Matt talked about that quite a lot. We have a large wavelength range and decent signal to noise even in the outskirts of our galaxies. We've constructed a luminosity-dependent, volume-limited sample, which is essentially complete down to 10 to the 9 solar masses. And we can weight the sample to be roughly flat in stellar mass and balanced in color at fixed stellar mass. We can also make it relatively uniform in terms of radial coverage for out to 1.5 effective radii for 2/3 of the galaxies and to 2.5 effective radii for 1/3. So if you'd like more details, there's this paper of mine from last year giving an overview, and then I just want to advertise Rinbin Yan's paper coming out later this year, which describes more details about the survey design and execution, and also presents a characterization of the initial data quality. We currently have a little more than 2,500 galaxies observed, and then the main point of this slide is to advertise the public data release coming this summer in July. We'll be releasing 1,400 unique galaxy data cubes. So I hope many of you in the room will be interested in using this fantastic data set. Okay, so let me wrap up. I presented what I think is a bit of a puzzle. We see evidence for high mass galaxies growing in radius, which seems consistent with this merger-driven hierarchical assembly picture that's important at the high mass end, but we're not yet really detecting it in mass. And so I think new insights on this topic from deep wide field imaging surveys like Hypersin PrimeCam are going to be really important, because for the first time they're going to allow us to detect and characterize those outer envelopes where perhaps a lot of the assembly is occurring. And then finally, I think IFS surveys like Manga are going to provide a nice global to local test by actually measuring the chemistry of stars in the outskirts and confirming that they were formed differently than the core components and assembled components. So let me stop there. Thank you.
Perfect. Questions? For that, Go.
Yeah, next question. So how do you reconcile the puzzle with other observations that show growth in the massive galaxies, and even the part that they grow in size? And my understanding is the best model to explain that is by minor merging, they're adding mass. It's just too little for us to be able to observe.
So my take on this is that the people who are studying size evolution are very careful about fitting profiles, because that's how they get their size estimates. But for those of us who study luminosity functions and mass functions, we typically use Quan radii or Petrosian flux estimates. And so we're not paying enough attention to the details of the light profile when we get our total masses and luminosities. And so for these kinds of studies, the good thing is that we're getting this amazing statistics in these new surveys. The bad news is that systematics are going to be the name of the game. So just being able to very finally understand your measurements and luminosity are going to have a big impact, I think.
Just a note of caution regarding the determination of the masses. In the high mass end of the galaxy stellar mass function, for example, for smaller galaxies, it could be a variation of more than a factor of 10 in the density, just because you are using different mass to luminosity ratios or different ways to estimate the mass. And this for higher ratios is even more dangerous. So I think it's it's important first to know how to determine the stellar masses of these massive galaxies in particular. Yeah?
I completely agree. I think it's the same point. Bernardi, work by Bernardi recently has really emphasized this. So you want to make sure you have a consistent way of extracting your total luminosities across the redshifts that you're measuring. So I completely agree.
Regarding the metallicity gradients and the H gradients, what type of signatures are you expecting in this scenario of external growing? Because it's not clear to me that you really find like a characteristic. You may find a gradient, but it's very difficult to separate between a gradient with a text like this.
Yeah, naively speaking, I'd like to see younger ages, because I think that low mass satellites that are still able to merge with these systems and build their outskirts are going to be forming stars at later times than the core components that are building up. And so I would expect there to be younger ages out there, but that's not what we've seen so far. So Jenny's evidence mainly comes from correlations with velocity dispersion, with K-band luminosity, and how those differ at different radii. So probably the fact that things are mixed up is going to be a big challenge to actually disentangle what's out there.
Thank you. Well, let's then, Kevin again.